Is everyone hearing me clearly? I need you to confirm if you're hearing me clearly.
Yes, I can hear you.
Okay, thank you so much, and thank you for confirming that. I want to welcome everyone to my lecture today. But before I get started today, I'm going to make this announcement. Midterm 2 will be uploaded July 16 by 8 a.m. I'm going to say that again. Midterm 2 will be uploaded, okay, July 16 at 8 a.m. And I'm actually going to leave that open for 24 hours. Okay, you can start at any time within the 24 hours window. I just want to let you know about that. There's going to be lab section tomorrow, and the material for that has already been uploaded. You can check the course module. Okay, so give me 1 second. I'm going to, share my lecture slide for today. Okay, I want to welcome everyone to my lecture today. Today, we're actually going to continue with time series analysis. You remember earlier in the week, we started time series analysis, and this is going to be the third time we're going to meet on time series analysis. And that is the reason why I'm calling this part 3. Of course, the focus today will be on AR models and ACF plots. So what do we mean by AR models? That's auto-regressive model, okay? And what do we mean by ACF plot? That is autocorrelation function plots. Okay, so that is going to be our focus for today. Okay, so I want to have a review on autoregressive model of order 1. You remember the last time we met, I actually walk you through autoregressive model of order 1. Okay, the autoregressive model of order 1 is basically relating the current value of the series to the immediate past. I'm going to say that again. By autoregressive model of order 1, we are actually relating the current value of the series. Okay, we are relating that to the immediate past. If you're talking about gas price, okay, maybe we actually want to relate the gas price today to the price yesterday. That's what I mean. If the unit of time is actually daily, the unit of time could be weekly. The unit of time could be quarterly. The unit of time could be yearly as well. So now that is what we mean by AR1, our autoregressive model of order 1. Okay, the other time I also show you the formula, of the autoregressive model of order 1. I remember I told you we can actually write it this way. Okay, you can write it this way, and we can also write it this way. Okay, so writing it in this way now, of course, we are actually subtracting the mean. Look, if you take a look at this guy now, so that is the mean of the model. Okay, we are subtracting the mean from the current value of the series, and we are also subtracting the mean from the immediate past value. Okay, so what I'm trying to show you now is autoregressive model of order 1. And of course, CO, actually, that is the intercept. Every model we basically have intercept, and of course the C1 here is the contribution of immediate past to the current, and the WT is what we call noise, because in any statistical model you're basically gonna have the combination of signal and a noise. And what we're actually trying to do is to filter out, the noise from the signal. We actually want to make sure there's no signal that is left inside the noise. Okay, so take a look at that. That is just the specification of the autoregressive model of order one. Okay, so the next thing I actually want to talk about now is if you take a look at what I have, if you take a look at what I have now here, okay, so what is actually telling you is that we already know the values of the C0 to be that. We know the values of the C1 to be that. So I'm also going to show you the way from the data set, part of what we're going to do today. I'm going to show you how you can estimate parameters in an autoregressive model of order one, just like what we did in linear regression, where we estimated, the linear regression parameter. I'm also gonna walk you through how you can actually, uh, estimate the parameter in the autoregressive model of order one. Okay, and of course, the parameter we actually want to estimate is so what is a C naught and what is a C1? You get what I mean? So that is what we basically want to find. And of course, if you take a look at this guy now, okay, this is another way to write a model. Okay, writing the model now. So it means we already know the mean, the expected value of YT if you follow what we did the other time. The expected value of YT is actually mu, which is equal to 8. Okay, so if you work on this now, that's basically what you actually going to see. Okay, that's basically what you're going to see. Okay, so that is a specification now. Okay, now you remember last time I also said we actually place assumption, on the noise. WT is actually noise. Okay, in time series analysis, we actually call that noise. Of course, in linear regression model, that is an error. That's what I mean. That is a place of unexplained variation in linear regression model. Okay, so assumption here now, when an autoregressive model is actually being given, okay, they're going to tell you what does it mean and what is the variance. So what this guy is telling you now is that the WT, the mean of that is equal to 0, right? So which means what it's telling you now is that the expected value of WT, don't forget the WT is actually noise, you get what I mean? Okay, is equal to 0. And of course, the variance, okay, the variance of, WT, okay, the variance of WT is actually is 0.19. Okay, that is what it's trying to show there. So I wanted to pay attention to that whenever we specify autoregressive model of order one or any time series model. We need to tell the world what is the distribution of the noise. Okay, I just wanted to take note, okay, of that. And you remember last time, when you are given, when you have this as autoregressive model of order one, okay, you can be asked to find the mean. Okay, take a look at the formula. I walk you through this the other time. It's just very easy. Okay, the mean is just going to be C naught divided by 1 minus C1. Okay, I wanted to take notes of that, in this model now. Your C naught is 15.2, your C1 is negative 0.9. Okay, by the time you plug that in, you got 8. Okay, that was how we got the 8 here, that you're actually subtracting, so now I call that 8 mu. You get what I mean? Okay, so for autoregressive model or for that one, that's a simple formula if you want to get the expected value of yt that we actually call the mean. Okay, now another thing that I'm actually want to talk about now is the variance. You want to get the variance of yt. There's a difference between the variance of yt and the variance of wt. Okay, if you take a look at this guy, give me 1 second. I'm going to clean up. If you take a look at this guy here, this is the variance of WT. Okay, the variance of WT, symbolically, we can also write that as sigma squared W. Okay, and right now is given to be 0.19. Okay, if you look at the formula here, you're basically going to say that the variance of yt, okay, the variance of the autoregressive model of order 1, if you want to find that, is going to be the ratio of the variance of the noise divided by 1 minus c1 squared. Okay, and that is why here you can see I'm actually plug in 0.19, okay, to represent this guy now, divided by 1 minus C1 squared. And of course, the C1 here is negative 0.9. Take a look at that. That's a C1, right? Okay, the variance of yt now give you 1. Okay, I think you understand that now. Okay, and of course, I also talk about the autocorrelation function. If you take a look at what I have here, okay, for autoregressive model of order 1, okay, the autocorrelation function at lat k, okay, I think I derive it to you the other time. It is C1 raised to power k, okay, it is C1 raised to power k, okay, it is C1 raised to power k. So, and for this model now, where C1 is a negative 0.9, I'm actually going to plug that in and raised to power k. For instance, if I want to find for instance, if I want to find the autocorrelation function at like 1, where k equal to 1, okay, I'm just going to do minus 0.9. Okay, then I'm going to raise it to power 1, so which is negative 0.9. Okay, so if I want to find at k equal to 2 now, so which is the autocorrelation function at log 2, or what I'm just going to do, I'm going to write that raised to power 2. So maybe that's going to give me 0.81. I can keep going like that depending on the one I'm actually looking for. Okay, so I just wanted to take note of that. But let me tell you this, this guy here is what we call theoretical mean. Okay, let me just say all of them. Give me 1 second. I'm going to say this because I'm also going to walk you through the sample one. So this guy, this guy, this guy, all of them, they are theoretical. Okay, I'm going to write it now. They are theoretical. Okay, they are theoretical. So what do I mean by that? Okay, 8 here, it means if I want to get the theoretical mean, I'm actually going to use this formula and that will give me 8. Okay, if I want to get theoretical variance, okay, I'm actually going to use the formula here, the theoretical variance of yt, and I'm going to get this. If I want to get the theoretical autocorrelation, okay, the theoretical autocorrelation now, okay, that's exactly what I'm gonna use this formula right here now, and I'm actually gonna get this. So all this now are theoretical because we're still gonna talk about the sample version because there's a difference between the theoretical mean and the sample mean. So if I want to get a sample mean, I need data set. Okay, I'm gonna walk you through how you can get sample mean from data set, how you can get sample variance from data set, and you can get the autocorrelation, at any lag from a data set. But the one I'm showing you now, they are theoretical one. Okay, they are theoretical one. I just wanted to know the difference between them. Okay, now I want to go into the practical one now, where we want to make use of the data set. Don't forget, if we really want to analyze, want to do time series analysis, of course, we're basically going to analyze data set. You get what I mean? So that's what we're going to do, right? Okay, we're going to analyze data set. Now, there's something I want to do now. Four of us want to, do something now. I want to try, try and get some data set to work with. Okay, and I'm going to show you how to simulate. Of course, I'm still going to walk you through this in the lab section. Okay, take a look at this now. You know what this is trying to tell me. Okay, I want to simulate uh data set. Okay, and in my simulation, this is what I want to take a look at. This guy now. You have a time series model, okay, giving us this. Okay, you have a time series model, okay, giving us this. How do we simulate the data set, as in YT? Simulation is more or less like, okay, if I have this model now, okay, what kind of data set was used in arriving at this model that I have right now? I want to show you now how we can actually do that. But there's something I wanted to pay attention to. We need certain parameters in our simulation process. If you take a look at, we need you know, a row with the minus 0.9 that you see here is actually the autoregressive coefficient. We need that. That need to be specified. Then we need the mean. Mean is 8, right? And we also need the variance of the white noise. Look at that. The white noise here is 0.19. So if I want to do the simulation now, if I want to generate my data set now, okay, I'm actually, this is the code now. I'm going to use what we call arima.sim. That is the code now. So here, you know what I'm trying to do? I want to generate 1000 data set. Okay, I want to generate 1000 data set. Okay, where the autoregressive parameter is negative 0.9 and the variance of the error is 0.19. Because when the variance is 0.19, SD is the standard deviation. Standard deviation is the square root of variance. I think you know that. Then plus the mean. Don't forget, the mean here is actually 8, right? Now, when I simulate 1000, because of the fact that if I simulate 1000 data set, and if you also write this same code, okay, since we're simulating at random, we're basically going to have different data set. I'm going to say that again. If you copy this into R now, okay, what you're going to get, 1000 data set you're going to get will be different from the one that I'm actually going to get. Even if you do that several times, you're basically going to have a different data set. Now, what are we going to do? If we actually want to have the same data set, then we need to set a seed. Okay, that is what you see here, set.seed. Okay, set.seed. When we're setting the seed, if we can put any number in the seed, but it has to be the same number. Okay, if I put 2 in my set seed, you're also going to put 2 in your set seed. And with that, we basically gonna have the same data set. I think I'm gonna demonstrate that now. I'm gonna open my heart. Okay, like I said, I'm still gonna walk you through this in the lab section, but you know what? Uh, I'm actually gonna show you, just gonna have a demonstration. Okay, I'm gonna copy this guy now. Okay, I'm gonna copy that guy now. But before I set a C, let me first show you this. When I copy this guy, okay, don't forget what I want to do. I want to simulate. I'm gonna open my R. Okay, I'm gonna open my R now. I'm gonna share my I'm gonna share R with you now. Okay. And I need everyone to confirm. If you are seeing my R studio right now, is everyone see my R studio? Okay, thank you so much. Oh, thank you for confirming that. I think it's only one person that confirmed now. I need another person to confirm. Okay, thank you. Okay, now, if you take a look at what I have now, okay, I gonna paste that. Okay, that is my code, right? So, that is my code, right? Now, when you take a look at this now, when I run that, okay, I'm gonna show you what my data said, YT. You saw a lot of data set. Okay, I've simulated 1000. Okay, if I don't set it, say, okay, I'm gonna rerun that again. You're gonna see. Because I have a lot of data, I'm gonna do this. Let me just so that I want to say the very first six. Okay, the very first six. Okay, now that is the very first six, right? That's something I'm gonna show you now. I'm gonna run this again and see. I'm rerunning that again. Okay, and I'm gonna see the first six. Now, if you take a look at the first six here, if you give me 1 second. If you take a look at this guy, right, and you take a look at this guy, they are not the same. That's what I told you. When you don't set a seed, we're basically gonna have different data set simulated. Okay, if you don't set a seed, okay, I'm gonna say that again. So if you don't set a seed, because we are actually simulating randomly, okay, we are simulating randomly. Okay, so that is what is going to happen. Okay, so because of that, I'm actually going to set a seed. Okay, I'm going to set a seed. Okay, let me clean my whiteboard. I'm going to clean my whiteboard now because I got a lot. Okay, so what I'm going to do, I'm going to write set dot seed, but we have to set the same seed. Okay, so set dot seed, or maybe I put two. We gotta make sure we put the same number if we want to have the same. Now I'm gonna rerun the code now. Okay, if I run this now, let me look at the first six. Okay, I'm gonna look at the first six data after setting seed. I got that right. Okay, now that I've set seed, okay, if I run this again, okay, and trying to look at the first six, give me 1 second. If I let me do this. At every time that I want to do it, I need to set seed. When I set seed, okay, I have a set dot seed too, right? Okay, I run this, okay, and the first says give me that. Okay, and I want to do that again. I set seed. I set that same seed, okay, and I run it. Then what is the first six? Now you can see that here, what I have here is what I also have here. Look at that. So that is the essence of setting a seed when you are simulating. Okay, so setting a seed is just like, okay, I basically want to have the same set of observation. Okay, that's what I mean. Okay, so we have our data set in place now. Okay, we have our data set in place. You get what I mean? Okay, we have. I'm gonna go back to the material now. Okay, I'm gonna go back uh, to the material now. Okay, and I need everyone to confirm if you are seeing my material right now. Is everyone seeing my material right now? Thank you so much, and thank you for confirming that. Okay, so when you take a look at this guy now, you know how to actually simulate data set. Now, what I want to do now, in time series analysis, part of what we did yesterday, we actually if I want to look at the behavior of the series, we need to generate time series graph, right? And how do we? And I told you yesterday, the time series graph we enable us to detect, you know, detect what we call the trend, the seasonality, structural break. I talked about that in my last lecture. Now, how do we, if I have a set of data now, okay, so how do I generate a time plots? Oh my God, this is the coding now, right? Take a look at that. That is the code, right? Plot.ts. TS is time series. Plot.ts. Okay, if I copy that now, okay, and I go back into R now, okay, if I copy that and go back into R now, okay, if I already have my YT, okay, give me 1 second. Okay, so take a look at that now, right? You've already generated that now. Take a look at that. You've generated that. This is a time plot now. This is a time series graph. Just gonna do plot.ts, right? Of your YT. Okay. Even if you don't want to do that, you can just actually, if I don't want to do that, you can just write, just plot into that. It should give me the same. Look at that. Even plot.ts of YT, you should be fine. Okay. So that's a time series plot. Okay. That's a time series plot. And that's what you have here, right? You can look at that, right? Now, when you have a time series plot now, I told you something the other time. Uh, one of the assumptions is that the stationarity, like the mean should be the same over time, the variance should be the same over time. The autocorrelation at any lag, at lag 1, they're supposed to be all be equal. At lag 2, they're supposed to all be equal. You understand what I mean? Now, the question now, I have data set now. How do I find the mean? Don't forget the other time I told you the mean here, there's a theoretical mean. 8 is a theoretical mean. Now that we have a data set now, okay, can we have a sample mean? Of course, if I want to have a sample mean, I'm just going to do mean into YT. Okay, so if you go back into the R material, you already have your YT. If you just plug in mean YT, now this guy here is a sample mean. Don't forget the other time, the theoretical mean was 8, right? The sample mean now is 8.01. They're actually going to be close. So what about the sample variance? And now I'm just gonna be VAR YT. Look at that. That's gonna be VAR YT. Okay, look at that. My sample variance now is 1.076687. Look at that. So I'm gonna go back to the material now. When you have the data set, you can actually find the mean, the sample mean, and the sample variance. Don't forget the sample mean and the sample variance here is actually different from here. Look at that. This is a theoretical mean, and this is a theoretical variance. The theoretical variance is 1, right? What do we get for the sample variance? The sample variance was 1.076887. Take a look at that. And that was why I said, since I simulated data, I know that my mean equal to 8. Initially, I used the fact that mean equal to 8 and the variance equal to 1 to simulate the data. But at the end of the day, when I have my data set, when I find my mean and variance, they are not the same exactly. I just wanted to know about that. But what I can see now, the values that I got, they are very close to the true mean. Let me tell you this. The theoretical mean, this guy here, the theoretical mean that we got and the theoretical variance, we normally call them true. They are the parameter, they are the population one. So I'm gonna come back here now. Take a look at this guy now, right? Okay, we can also call that population mean. We call that population mean. You can call that theoretical mean, or you call them population mean, or you call it true. Okay, true mean. Okay, this one here, theoretical variance or population variance or true variance. The theoretical autocorrelation or true autocorrelation, because we're also going to get a sample one. You get what I mean? We're also going to get a sample one. Now I've walked you through how to get a sample mean, sample variance. Now the next thing now, let us also get the autocorrelation, okay, from the data. I've walked you through how you can get the autocorrelation, the theoretical autocorrelation for AR1. You're just going to use this guy 1C1 raised to power K. Do you know what I mean? That is the theoretical one. Do you know what I mean, right? What if I now have a data set? I have some data set now. And what I want to do, how do I get the ACF? Oh my God, that's a simple code. But I'm going to show you the ACF, the way the ACF is going to look like. It's going to look like this. But you know what? If I want to do that now, that's go easy, right? This is the code right here. Do you see the code? When you already have your data set, you're just going to write ACF into YT. Okay? That's what you're going to do, right? I'm going to, if I copy this guy now, okay, I'm going to copy that guy and I'm going to copy that into my app now. And you basically going to see. It's going to be super easy, right? Okay, now I'm going to give me 1 second. Now, that's my house studio, right? Now, let me post that now. Okay, ACF is just a function, the coding out to get a sample autocorrelation function. Now let me plot that. Oh my God, look at what I got now. Okay, this is the ACF. Look at that at different lag. Okay, and if you go by what I told you yesterday, right, at lag 0 is always going to be 1. Okay, and you can see it's actually going down, right? It's decreasing, right? As lag is increasing, okay, and that is going to give you, that's going to suggest to you that probably you're working with the auto-regressive model of order 1, okay? So probably you're working with the auto-regressive model of order 1, because if I really want to identify, the whether auto-regressive model of order 1 or auto-regressive model of order 2 or order 3 for data set, the only condition for me to know whether I'm working with the auto-regressive model of order 1 is when I generate an autocorrelation function plot and I realize that that is actually going down as lag increases. The autocorrelation function is decaying. That's what we call is decaying. Okay, now you know how to do the plot now. So I'm going to go back to the material. Now on the material now, so I've already told you, okay, we've already generated that. And when you take a look at this material now, okay, uh, you'll be able to tell, each of these will represent, like this is at lag 0, right? This is at lag 1. You can read that at lag 1. Is that at lag 2, lag 3, and so on like that. Okay, the blue lines are the 5%, you can see the blue dotted line here, right? the blue dotted line are the 5% significance limit for testing the autocorrelation equal to 0. Okay, for testing the autocorrelation equal to 0, you can see here, majority of these are actually beyond that. So which is, don't forget, when the autocorrelation equal to 0, it means the model is an entirely white noise. I'm going to say that again. When all the autocorrelation, I showed you the other time, if I have lag 1 is equal to 0, lag 2 is 0, lag 3 is 0, if all the lag, if the autocorrelation function for all lag equal to 0, then it means your model is an entirely white noise, and that is not going to be a good model. Okay, but now, okay, of course, they are not 0, okay, but only that, as lag is going up, of course, we expect, when the autocorrelation is going down, there's no problem about that. That's an indication of the AR1 model. That's what it means. Okay, I want to move right now. You know, if from what we got, if you really want to have access to each of the values, okay, of the autocorrelation here, okay, if you want to have access to each of those values, I can just write the ACF YT plot F. Okay, give me 1 second. I'm actually gonna, go to R now. I'm gonna paste that. Okay, when I paste that now, give me 1 second. I paste that now. Then you can see now it's gonna give me autocorrelation for up to 30 lag. Don't forget here, I have from 0 to 30, right? Okay, so each of these value now actually represent the autocorrelation value at a particular lag. Okay, that is how you're going to get it. And don't forget, this is sample autocorrelation. Okay, this is a sample autocorrelation at different lag. Do you know that we can also use, we can go back and use the formula right here. Give me 1 second if you want to get the theoretical one. If you want to get the theoretical one, all what you just need to do here at lat k, when k equal to 0, plug that in, that will be 1. Of course, at lag 0, the theoretical autocorrelation and the sample autocorrelation, they're going to be the same. They will give 1. But at every other lag, they are not going to be the same. Because if you plug in 1, plug in 2, up to 30 here, you're going to use this to generate. You can calculate the theoretical autocorrelation. Okay. And of course, I just show you how you can calculate the sample one. Okay. Now, if you generate that, I'm going to show you when you compare them. Okay. When you compare them, take a look at here. This is where I'm trying to compare them up to lag 7. Okay. If you take a look at this guy here, this is the one that you use C1. Okay. Raised to power K. Okay. And your C1 given in the model was a minus 0.9. Okay. Was minus 0.9. When you plug in 0, at like 0 is going to be 1. Okay. When you plug in 1, this is what you have. When you plug in 2, this is what you have. When you plug in 3, that's what. So this here, they are the theoretical one. But this one here, these are the one you get from the data, from the sample. And that is why you see a cap here. That's an estimate, right? This is an estimate. Okay. I wanted to take note of that. So the estimate, you got this one from the sample, right? And you got this one from the formula. And that is the reason why I actually call this guy here theoretical autocorrelation. Okay. Or we call it theoretical autocorrelation, or you can also call it population autocorrelation. This is the sample one. Okay. The one we got from the data set is the sample one. Is there anyone who need clarification about what I said right now? Is there anyone? Is there anyone? Any clarification about that? If you guys are good with my explanation, I need you to say yes, or you comment yes. If you are good with my explanation now, okay, thank you so much. But you know what? If you don't understand, please ask question. You pay for the service. Now, as you can see now, you can compare them. Okay. And you know what? Like I said, the estimated, look at that. Look at what I estimated autocorrelation values. The estimated one is this guy here. Okay. So how this one, because we got that from data set using the code that I showed you the other time. So these are the estimated one. Okay. That is the estimated one. But if you take a look at this guy, that is the true values of the autocorrelation, the population one, the one we use the formula C1 raised to power K. And you know what? We just want to see, is there going to be a kind of a significant difference between uh, the estimated one and the true values? That's what we're trying to say, to compare them at different lag. Okay. So take a look at that. Now you know the difference between the estimated one and the true one. Okay, now you know what I want to do now. I want to go into simulation. I want to go into how do we, when we have data set. Let's say, for instance, you have data set. Okay, the data set could be, gas price over time. It could be stock price. Could be sales, volume of sales, could be production over time, and so on like that. If you have data set that are collected over time, how do we actually fit an autoregressive model of other one? That's what I want to walk you through now. Just like you have a linear regression data, you have a Y and X, and you basically want to fit linear regression model. If you want to do that, you basically I walk you through that in R, how you can actually implement that in R. So we also want to do the same now. When we have data set, this is time series data, and we basically want to fit time series model. And the time series model that we want to fit now is what we call the AR1. So which means on the time series model, we want to figure out what is going to be the C naught, what is going to be the C1, and what is going to be the mean. And how do we going to do that? This is the code in R. If you want to do that, we call that ARIMA. ARIMA, okay? ARIMA actually means autoregressive integrated moving average model. I'm going to say that again. ARIMA here means auto-regressive integrated moving average model. That's what it means. But you know what? There are three combination of models in ARIMA. There's AR, okay? There is AR. You have integrated that we call differencing, I, and we have the MA. We're still going to talk about moving average models. But you know what? When I want to do AR1 means ARIMA 100. Okay, the ARIMA, like I said, ARIMA can be splitted. Like, take a look at this. I got ARIMA now, right? ARIMA, I can split that into AR, into differencing, and into MA. So if I want to talk about AR1, it means 1 here, differencing is 0, then I'm not considering moving average. That's why you see 0, 0. That's why you see 1, 0, 0. Okay. YT is my data set. Is the times, the time series data. Okay. I just wanted to take note of that. Okay. If I want to do a AR2, it's going to be ARIMA 200. And if I want to do differencing, then if I difference one, because, what is the essence of differencing? Maybe my data set is not stationary. Okay, if it's not stationary, I can do the force differencing. Okay, if I do the force differencing and it actually attains stationarity, it means my differencing is going to be 1. I can have ARIMA 1, 1, 0. I can have ARIMA 2, 0. So there are different form of that, right? But the AR1 here is going to be ARIMA 1, 0, 0. That's exactly what I mean. The arrow of that is 1, the other on differencing is 0. We don't, when the data set is stationary, we don't need to difference that. I'm still going to walk you through differencing. Okay. And we also have another set of time series module that we call the MA, you through differencing. Okay. And we also have another set of time series module that we call the MA, moving average model. But right now, we're not interested in that. We're only focusing on ARO of order 1. Okay. Now, this is the code in R. I'm just going to write ARIMA into my model. If I write this guy now, if I copy this guy now, I already have my data set, right? And I'm gonna go into R right now. I go into R, okay, and I'm gonna clean this now. Then I'm gonna copy that, okay. Then I'm gonna run that. Then what is the summary now? Okay, where I do the MOD, just say MOD. Okay, what do you have? They can look at that. This is the result now. What is it giving me now? You know what is giving me now? Okay, there's something I want you to know. Okay, in ARIMA mode, when you run a time series model, okay, this guy here is a C1. Okay, that is a C1. But the intercept here, this is not a C0. But this one that appear in the intercept in the model is the mu. Take notes. That is the mean. I want you to take note of that. It's not the intercept. Just like what you have in the linear regression, it's different from linear regression where you're going to say, oh, that one is my beta. Not. Here it is not. It's representing the mean. I'm going to say that again. It's representing the mean. Okay. You need to find a C0 yourself. I'm going to show you. Okay. Now you can see the output now, right? And here, these values here are just the standard error. The one here, SE. That is the standard error, right? And every module is basically going to come with the AIC. Okay. We're going to have a log likelihood, and we're going to have the sigma estimated. They're always going to come with the model. Okay, so I'm going to go back to my material now. Okay, that is how that is estimated, and that is what you can see here. Take a look at that. Okay, this is the C1. Okay, this guy here is 8.0134 is the mean. I want you to take note of that, right? Okay, and if you take a look at this guy now, this is the estimated sigma squared. Okay, estimated sigma squared. Okay, with we're talking about if I ask you the variance of the residual or the variance of the noise, it's this guy here. Okay, that will be part of the output. Okay, now this is what I was trying to say. I said this is mu cap. Okay, the estimate of the mean. Okay, and this is a C1. Now, if you have an output like this in R, and I say, okay, write down the fitted AR1 model. If you want to write out the fitted AR1 model, this is the formula, right? Take a look at that, right? Okay, that is the formula, right? This is the population one, right? And this is the fitted, right? Don't forget I told you the other time the fitted is the one you use on your data set. Okay, on the data set right now, okay, you're actually going to be talking about this guy. Now, what are you going to do now? What you're basically going to do, you're going to look at the model. Okay, why do I write 8.01? That is a mu cap, which is this guy here. Look at that. To 2 decimal, right? What is a C1? Negative 0.901 or 0.91 to 2 decimal. That's what I plug in there. Look at that. It's easy now. Now, you know, from here now, this is a fitted model, right? Okay, this is the one we've been using before. Okay, because before we just been assuming value for C1 mu. The value we've been using is the one from population. That's why it's population model. There's no cap. But now that we're working on the data set, they're going to have cap. And I just plug them in. Look at that. When I plug them in, Okay, and you now simplify. If you simplify this guy now, okay, I'm going to show you. Then if you simplify that, you're basically going to have this, okay, which means I just got my C0. My C0 did not come from the output. My C0 actually come when I simplify this. Now let me show you, I'm going to show you how to simplify that guy. We got a white T cap, okay, equal, minus 8.01, right? Okay, that's equal. If I multiply that by that, that's going to be minus is 0.91 yc minus 1, right? Then if you use this to multiply that, that's going to be a plus. All what you just need to do is, let me use my calculator, 0.91. Give me 1 second. I'm going to use my 0.91 times 8.01. That would be 7 points. So here I'm actually going to have 7 point 2.891, right? Okay, so when I have that, so what do you think I'm actually, so if this guy should go to the other side, of course, I'm actually going to have YT cap equal, so I'm going to have this guy plus this guy by the time it's coming. That's why you see this guy, 15.30. Then I'm going to have this guy. That's why you have this guy here now. So this is my C naught, and is 0 .9 is my C1. So you can see that now, right? Okay. So the C naught is doesn't come with the output. It doesn't come with the output. You're gonna be the one that will solve, that will simplify, and you're basically gonna have this. Okay. Now, is there anyone who need kind of clarification on this? Is there anyone? Is there anyone who need a clarification? If you're good with my explanation now, I need you to say yes, or you comment yes. If you're good with my explanation now, I need you to comment yeah. Okay, thank you so much. Thank you for understanding me. I'm basically gonna move now. You can see now with now simulate estimated, we've gotten the AR of order one, the auto-regressive model of order one from data set. Now, this is the model that we have now, right? Okay, that is a model. So which means if I want to make a prediction now, okay, the current value of the series is YT cap. I can predict that if I plug in the immediate past value. I don't put a cap on this guy, right? Because we already have this guy, right? So we can predict that guy from that. Get what I mean? Okay. Now, when we, in linear regression model, when you actually have a fitted model, how can we trust our model? We do diagnostic checking, right? We do model diagnostics. Okay, if you want to know how poor your model is or how good your model is, we're basically going to revisit whether assumption is violated or not. We're also going to do the same here. Okay, this is a model, right? How good? Before I can use it to make a prediction, I actually need to investigate whether the model is fantastic or not. And if I want to do that, and that's what I call the model diagnostics. Okay, so if our model actually fits the data well, then we expect residual to behave like a white noise. Okay, and when what do we mean by residual behaving like a white noise? It's, in other words, what we mean is that you don't have any signal again left in the residual, because in statistical analysis, we basically want to filter out the signal from the residual. Okay, so that the residual is going to stand alone. There's not going to be any signal. There's not going to be any signal inside that. Okay, and the only way to tell You remember in linear regression, what we use residual plot, right? We're also going to do that here. Okay, so what you're going to do, you generate a residual plot. Take a look at this. This is the code, right? If you put that, if you copy that and paste that in now, okay, you're going to have this. Now, what is the behavior? What are we expecting? Okay, we are targeting residuals, right? For residual to behave well, okay, they should be the mean. You remember in uh, assumption, we expect the mean of the residual to be around 0. Don't forget, when we are specifying, uh, noise, we said is high ID, okay, follows normal distribution, which means 0, and variance sigma squared W, right? Okay, so what we're trying to say, it should be around 0. Take a look at this. You're going to see that this is around 0, right? That is fluctuating around 0. Okay, so situation where that happen, okay, then it means your it actually behave well. That's what we mean, and that is what I'm trying to say here. Okay, I said the averages of the residual are approximately 0. Okay, and not only that, the variability of the residual does not change. Not just like what you have in linear regression. In linear regression, when you use residual plot, of course, in linear regression, it is different. Before you can actually say expected value of error equal to 0 in linear regression, you expect that the residual plot shouldn't show any pattern, right? I'm going to say that again. Residual plot shouldn't show any pattern, okay? That will shows that, assumptions of linearity hold, right? In linear regression, right? But in time series analysis, when you generate residual plot, okay, the averages of the residual should be approximately 0, and the constant variance still hold. The same. In linear regression, we have a constant variance. We said the variance of the residual, different values of the predator have to be the same. Okay, we are retaining that because here, okay, don't forget in time series, we also have that assumption of stationarity. We expect that the variance should be constant over time, right? And as you can see here, it is constant over time. Take a look at that. And that was why I said the variability of the residual does not change. So which means the both of the scenario now are consistent with the property of the white noise, because that is what we expect. Okay. Now, another way you can actually check is to generate the autocorrelation for the residual. Let me tell you this. Okay, one of the diagnostic testing, one of the way to investigate whether our model is actually doing good, before we can actually make prediction with the model, we need to generate the autocorrelation function of residuals. Autocorrelation function of residuals is different from the autocorrelation function of the series, of the time series. I'm going to say that again. There's a difference between the two. Okay. Here now I'm talking about the autocorrelation function of residuals. And what do you expect for autocorrelation function of residual for not for the residual to behave like a white noise? Oh my God, for residual to behave like a white noise, we expect at every lag, okay, the autocorrelation should be 0. I'm going to say that again. For residual to behave like a white noise, because we actually want for model to be fantastic, for the autoregressive model that we are actually considering now to be fantastic, we expect the autocorrelation function at any lag for residuals to be equal to 0. Now, I want you to take, if you copy that into R, this is what you're going to have. You're basically going to see, of course, it is only at lag 0 that is expected. Any model, generate the ACF of any series at lag 0 is 1, but at every other lag, Okay, if the for residual to behave like a white noise, none of that should be outside the blue dotted line. The blue dotted line is zero. And let me tell you this, at time we create room for error. Okay, if not more than 5% of them that can outside the line, we are still fine. We are okay. Okay, but the one I'm showing you now, you can actually see all of them are within. Okay, well, all of them are within, the blue dotted line. Okay, which means the autocorrelation function at like zero for residual. The autocorrelation function at any lag for residual is approximately zero, as you can see. But I told you, uh, at like zero is always one. That is the only one that we allow to come out. Though we can still have some that can be outside, but they should not be less than 5% of the whole thing. Because in statistics, don't forget, we have error we can tolerate 5%. That's why we use level of significance to be 5%. Okay, I wanted to take notes of that. So the ACF plot of the residual that I'm showing you now confirm that the residuals are behaving like a white noise. Okay, they are behaving like a white noise. Okay, if you look at the every other lag beyond zero here, okay, they all have, estimated autocorrelation function values approximately zero. Okay, so then with that, we actually going to say, okay, since the residual behave like a white noise now, of course, we can trust our model. We can trust the AR1 model that we estimated before. Now, I want to take you into an example, a real life practical example now. I'm going to take you to a real life situation now. Okay, I'm going to talk about the Google stock price. But before I move on, I need you to confirm again. Is everyone still hearing me clearly? Is everyone still hearing me clearly? Thank you so much. Thank you for confirming that. I want to walk you through an example now. Some of you have heard about stock, the SP 500 and so on like that. Some of them are determinants of economy. Okay. So I don't know whether you've heard about New York Stock Exchange, European market stock and stuff like that. Okay. So I want to apply, because there are data sets that are generated over time and, there's a lot of volatility in the market. And the question now, if I want to buy stock, as an investor, if you want to go into a market, you need information about the market, about the price of stock. Okay. And of course, I want to use an example, a real life practical situation now. Google stock price example. Okay, so this is a daily adjusted closing price of Google stock. The data set that we actually want to use here, span between April 22, 2018 to April 22, 2019. Okay, so this is the code. I'm gonna walk you through that now. Friday, take a look at that. You need to for generate a time series plot. I told you that is a part of the preliminary investigation. You want to understand your data set, you need to generate time series graph. Okay, the name of my data set is GOOG, right? GOOG. Okay, I'm just going to do plot.ts GOG, and actually that actually give me this. Look at that. Initially it's going up, it's going down, it's going up. Take a look at that. That is what we actually expect in a stochastic world. Okay, so that is a time series plot from the original data set. Now, the next thing I actually want to do now, okay, if I really want to know whether I should fit a particular time series model, or whether if I want to when I want to fit the auto-regressive model or moving average model or the auto-regressive moving average model. So what I'm first going to do after generating the time series graph, which is a preliminary, which is part of the preliminary investigation, I'm basically going to generate an ACF plot. Now the ACF plot here now here is this is not the ACF plot for residual. This is an ACF plot of the original series. You know, the essence of generating this ACF plot here is just to look at the behavior of the autocorrelation function as lag increases. Because before we can actually use an autoregressive model of order one, okay, we need to generate an ACF plot using this code. When you generate an ACF plot, if you see that the autocorrelation value as lag increases is going down, that we suggest an autoregressive model of order one. Oh my God, in statistical analysis, we don't just fit statistical model. Okay, we don't just fit a model, we normally do a lot of examination, and of course we have a criteria that we actually guide us on whether we should fit this model or not. Don't forget, initially I told you we find ourselves in a stochastic world. We live in a probability space, and you know what, things happens in the world so far, so fast. There's a lot of variation in this world. And how do we actually understand this world? How do we take a decision we're not going to regret? We're basically going to use an appropriate model, a statistical model to capture reality. That is exactly what we're trying to do. Okay, but we got a criteria to choose a model for data set. We don't just use any model. Okay, so on the that on based on the ACF plot now, I can see that the ACF is actually, as lag increases, the ACF is actually going down, and of course that could be an AR1. Okay, the fact that we say this and we are suspecting that that is going to be an AR1. Okay, well, after fitting the AR1, we're still going to investigate. Okay, whether that is truly AR1. The fact that a police actually pull you over does not mean you're going to be found wanting or guilty at the end of the day. Okay. I'm going to say that again. If you are driving and police pull you over, there's possibility after conducting this investigation, he's going to let you go without giving you any ticket. You get what I mean? Okay, the fact that we are suspecting AR1 does not really mean it's going to be AR1. Okay, when we after fitting our AR1, we basically we still need to do what we call model diagnostics. We're going to diagnose that, and we're going to investigate whether it is truly AR1. But right now, because I generate my autocorrelation function for the series, and I can see as lag is increasing, the autocorrelation value is actually going down, and that is one of the property of AR1, and that is why we are actually thinking that that should be AR1. And after that, you know what we're going to do next? We're going to fit AR1 to the data. You can see now, you see where I'm coming from? I don't just fit a model. Okay, I have to go through some, what I call data exploratory analysis, where I want to understand my data set. I used to tell students and I used to tell people around me, uh, statistician to data set or data scientist to data set is more or less like a doctor to patient. I'm going to say that again. The relationship between a statistician or a data scientist and a data set is the same. It's more or less like the relationship between doctor and a patient. Before a doctor can successfully treat a patient, the doctor must understand, you know, everything about the patient before he can successfully, you know, administer right drug, okay, for the patient. The same thing here that we do in statistical analysis, we need to first understand our data set. And that was the reason we don't just feed a model, we do some data exploratory analysis. We started by generating a time series graph. Then from there, we look at the autocorrelation function, because we're working with a time series model or with a time series data. Okay. So, and the autocorrelation function of that original series, we actually tell us whether we're going to fit AR1 or not. Okay. And since we actually generate the ACF plot and the autocorrelation of values as, as the lag is increasing, you can see the autocorrelation value was going down, was decreasing. Because of that, we're actually going to fit an autoregressive model of order one. And this is the code. Okay. So when you do that, oh my God, this is the result. Now, this is the output, right? Okay. So there's something that is very, very important in this output. Like I said, in this output right now, this guy here is your C1. Okay. The estimated C1. This guy here is the estimated mean curve. Okay. The estimated mean. Okay. Okay, this guy here, they are just the standard error. Okay, and this is the estimated sigma squared. Okay, so this guy now is actually the sigma squared W. Okay, which is the variance of the white noise, the variance of the noise, 310.2. That's the estimated one, right? And every model, you're actually going to have an AIC. The idea behind the AIC is just like, okay, if you have more than one model, okay, if you want to, for a time we could have situation where more than one model may be appropriate for a particular time series data, and maybe you're basically looking for the best one. Of course, you can compare them using the AIC. The one that have the lowest AIC is the best. I'm going to say that again. A model with the lowest value of AIC is actually the best. I remember before when I was walking you through model complexity and model fitness. Of course, I talk about the more criteria, the AIC, the BIC, and the adjusted out square, right? Okay, so this is the output now. Okay, that's what we're getting now. We actually do that for the GOG, the stock, the daily adjusted stock price, the Google stock price. Okay, now if I want to write the fitted model now, okay, because you can never make a prediction without first writing out your fitted model from the output. Okay, so don't forget, the model is basically y cap minus mu, okay, minus mu cap, okay, the yt cap, okay, minus that equals C1 cap. Don't forget about that. Okay, then the yt minus 1. Okay, then the entire thing minus mu cap. Take a look at that. That's a fitted model. So right now, okay, this guy here is a mu. I told you is the mu. Okay, this is a mu. I told you that's a mu cap, right? I plugged that in. Okay, and this guy here is a C1 cap, right? Okay, from the output. Okay, that's why you see, I'm taking that to decimal. That's why you see this guy here, and this is the mu. And don't forget, I told you the other time, you basically need to simplify this model. Okay, when you simplify this model, you're going to end up here. So this is the final model. This is the one you can use to make a prediction now. Okay, that's a final model now. Take a look at that. That's a final model now. Okay, now this is the model now that we have generated for the the daily adjusted Google price. Okay, where the YT cap, if I want to make a prediction about what the current price of the stock is going to be, okay, I can use this model now. Take a look at that. Okay, that is the way that is done. And the next thing I'm actually going to do, don't forget, we cannot use this model for now to make a prediction until we subject the model to diagnostic testing. I'm going to say that again. Okay, it's not as if our model are failing us. We are the one that we're not doing the right thing. Okay, if you don't actually subject the model now to diagnostic testing, how are you going to know whether the model is going to do a great job? Okay, so we're going to subject this to diagnostic testing, and what we're going to do is trying to test for residual. What we're going to do is we're actually going to get the autocorrelation function for residual. That's what we're going to do. I told you in time series analysis, if you really want to tell whether a time series model is going to do a great job, then you need to investigate the autocorrelation function of residual. Okay, we basically want to see whether the residual behave like a white noise. We basically want to see whether we have succeeded in extracting or filtering out the signal from the noise. Okay, and that is what I want to do here. Now, the very first thing as part of the model diagnostics right now, I'm actually going to get a time plot for the module residual. I basically want to see whether that is around 0. Okay, as you can see, this is around 0. This is a plot. Then the next thing I'm going to get the ACF, the autocorrelation function of the residual. Okay, I told you the other time, the autocorrelation function at 0 is always going to be 1, is the only one we're expecting out. Okay, we expect that all of that should be within the blue dotted line. But we also give room for error. Okay, if less than 5% is out, there's no problem. Okay, we're also going to give room for error. As you can see now, look at like 10. That is out, right? And at like 23, that is out. Okay, and that's what I'm trying to say here. Okay, at like 10 is out, at like 23 is out, but that's still fine. You know why? Because how many observations do we have? If the 5% of that is out, there's no problem. If I want to calculate, I got 23, we consider 23 lag, right? For 23 lag, okay? We actually, if you multiply 23 by 0.05, that would be 1.15. Let's say approximately 2. And we only have 2 out. If 2 is out, there's no problem. Okay, and that was why you said we have 2 that is out, and this is not far from the expected value 1.15 using a 5% threshold. So we can conclude that the residual behave like a white noise. And if residual behave like a white noise, you know what that means. Then it means we can go ahead using this model now to make a judgment, to make a statistical inference. That's what it means. I'm going to say that again. Before you can actually use your model to make an inference, to make a judgment, you need to first make sure you actually plot the residual, okay? And you plot the ACF of the residual, and you got to see that, okay? Okay, so since that happened, then we can now go ahead and make a forecast. What do we mean by forecast? Of course, the forecasting means scientific prediction. We want to make prediction of the future price. Okay, the Google stock price using the model, right? Okay. Now our data, and don't forget before we come to the forecast, we got to make sure everything is nice. Like the the noise is a white noise. The residual behave like a white noise, and of course, I just walk you through how you can investigate that using the autocorrelation function of residual. Okay. Now we want to make a prediction now because the model is good. We can go ahead making a prediction. So our data include the daily adjusted closing price of Google stock. Don't forget, from April 22nd, 2018 to April 22nd, 2019. In all, we have 251 observations. Okay, in all, we have 251 observations. But let me tell you this, before you can make a future prediction, why can't you try and make a prediction that we already know? And how close is our prediction is going to be with the one we already know? I'm going to tell you now. If you look at the last number in the observation, number 251, that last number from the data set is actually is this value. We already know that. We are using 251 observation. Okay. And if you want to use the last one, that is the daily adjusted closing price for April 22nd, 2019. Okay. April 22nd, 2019. the last observation. You get what I mean? Okay. April 22nd, 2019. Okay. Or what you're just going to do, if you plug it in here, right? Okay. Now, this is what happened. We already know, this guy. Okay. Now, if you take a look at this, if I set it to be 252, okay, this is what I have, right? Now, what do you think I want to do now? If you put 252 here, 252 minus 1, you have the. Now, we already have this guy, but we want to predict it. Okay. Now, if you make a prediction now, okay, the Y of 251, we know, let me just say this. We know this guy, the last observation, the Y of 251, okay, which this guy correspond to what happened on April 22nd, okay? And you know what we want to do now? We want to use it now. We want to use this guy to predict, okay? We want to use that guy now to predict for the second day. We want to predict April 23rd. What are we going to do? Okay? We want to predict April 23rd. Okay? Now, but the very first thing we need to first do to predict April 23rd, okay? Of course, we know what happened in April 23rd, 2019. We already know that, but we want to make a prediction using our model. Okay? Now, what are you going to do? Since for Y251, okay, if you plug that in, we already know that. Okay, this is going to give us this value. You see that? Take a look at that. Okay, don't forget the 251 is the last value in our data set. We want to use the last value in our data set to predict for 252. Observation number 252 will be for April 23, 2019. And when we plug that in, that actually gives us this. That gives us this. Now the question now, okay? This is when you just use a manual one. If you don't want to use a manual, if you want to use code, it's going to be predict mode, and ahead means you are predicting 1 day ahead. Don't forget, we want to predict for day 252, which will correspond to April 23, 2019. Okay, after making that prediction, this is what we have. And of course, if you use the arrow will actually show you this. You see the same thing, very close. Take a look at that. This is what the formula give you. This is what the arrow is going to give you. Now, if you now want to know whether your prediction is very close to what happened, then we need to go into the data set, like, okay, what happened in real life on April 23, 2019? What happened in reality? Okay, and what happened in reality was actually this. Okay, this is our predicted value. This is what happened in reality. This is a true value. What happened in April 23, 2019. This is what happened, and this is it predicted. This is what happened, the original value. This is a predicted. Now, if you now want to know our residual, we can subtract that and see the gap. Look at that. Okay, when you subtract predicted from the original value, that gives us this. Okay, that value is very, very small, which is about 1% of the price. So our prediction is not bad at all. Can you see that? Our prediction is not bad at all. And you know why I know? Because we've already done the autocorrelation, we've done the the diagnostic investigation, where we generated the time plot for the residual. We generated the autocorrelation function for residual. And of course, we saw that the residual behave like a white noise. If the residual behave like a white noise, there's not going to be a huge gap between what we predict and what happened in reality. Take a look at that. So time series analysis, of course, can actually will enable us to answer some question that has to do with the behavior of stock price, the behavior of gas price, and so on like that. When you have data set that are collected over time, that is the takeaway. Okay, so this is where I'm actually going to stop today. We're going to meet in the lab tomorrow. There's going to be a lab tomorrow. Of course, July 16 is when I'm going to post the exam. You can check the syllabus and check the announcement section. So I want to appreciate everyone who have attended my lecture today. I hope you enjoyed it. Until next time that we're going to meet again, don't forget there's going to be a lab section tomorrow. Okay, and the material for the lab session tomorrow is already uploaded. I call it Lab 6. Of course, I'm actually going to walk you through how to implement time series in R. Like I said, the time series is very, very easy. Very, very easy. And of course, this video, this lecture is being recorded. Of course, I'm actually going to, publish this before the end of today. Okay, make sure you stay safe and have a lovely day. So bye for now, everyone. Thank you too. Yeah, thank